So our next speaker is Elena Caviglia from the University of Leicester, and she will be speaking on what is a two-stack.
Thank you very much for giving me the opportunity to speak here. So my talk will be about an original notion of two-stack, which is a three-dimensional sheaf. And I will start recalling the usual notion of stack, and then I will tell you how to generalize this one dimension higher to get a notion of two-stack. I will then conclude by giving what is the motivating example for me. So let's start from a one category C with pullbacks. And the first ingredient that we need is that of a sieve. So given an object C of the category, a sieve S on C is just a collection of morphisms with codomain C that is closed under precomposition. And we also have a useful characterization of the notion of sieve. In fact, the sieve is, can be seen as a subfunctor of endow C. And so it is a natural transformation from a functor that I call RS, that assigns to every object of C the set of arrows in the sieve with domain that object, to endow of C. And using sieves, we can define Grothendieck topology on the category C, which is an assignment for every object of the category of a collection of sieves that we call covering sieves in a way that satisfies some conditions that are that the collection of all morphisms with codomain C is a covering sieve, that covering sieves are closed under pullback, and that being a covering sieve can be checked locally, where locally is with respect to morphisms in a covering sieve. And the next ingredient that we need in order to define stacks is that of a descent datum. So if we have a pseudofunctor f from C up to cut, and S is a sieve on an object C, a descent datum on S for f will be an assignment for every morphism in the sieve of an object WF in the image of the domain of this specific morphism, and then for every pair of composable morphisms where the second one is in the sieve, we have an isomorphism between G star of F, which is the descent along G of the assignment for F, and WF composed with G, which is the assignment for the composite of F and G. Moreover, we need a condition that is called the cocycle condition that says that every time we have a chain of morphisms like this one, where the last one is in the sieve, we have a commutative diagram. And this commutative diagram is essentially saying that if we consider the isomorphism of descent along G, and then we post-compose it with the isomorphism of descent along H, we obtain almost the same thing as considering the isomorphism of descent along the composite of G and H. And this isomorphism that we have here is a canonical isomorphism just given by the fact that F is a pseudofunctor. And we will need later to remember this notion of descent datum because we will see it in different flavors. Moreover, we say that a descent datum is effective if we can find an object W in the image of C this time, and the sieve is on C, that allows us to recover all the local assignments that we have, in the sense that for every F in the sieve, the descent along F of this object W is up to isomorphism W of F. And also these isomorphisms that we give are compatible in the sense that if we have a morphism G, we have the following commutative diagram. And if you look at this diagram, this looks really similar to the diagram of the cocycle condition. And this is because we can think of this global object W as the assignment of the descent datum for the identity of C. Of course, the identity of C is not always in the sieve, so we don't have W identity of C in general. But this global object W, when the descent datum is effective, behaves like the identity of C. And this is what this diagram is saying. So now that we have all the pieces, we can define the notion of stack. So a pseudofunctor from CTOf to cut is a stack if it satisfies this condition. Every descent datum for every covering sieve is effective. And then we have other two conditions that put together are saying that F is a sheaf on morphisms. So the first condition is saying that given two objects in f of C and given for every morphism in the sieve S a morphism from f star of x to f star of y, and in a way such that these morphisms are compatible with respect to composition, then we can find a morphism from x to y such that f star of this morphism is the assignment for every f in the sieve. And this is saying that the matching families for morphisms, that every matching family for morphisms have as an amalgamation. And then we have another condition that is a uniqueness condition that is saying that if two morphisms agree locally, then they agree globally. And this is saying that the amalgamation that we find is unique. And this definition of stack is very nice, and it's easy to check that something is a stack because the conditions that we have are very explicit. But if we try to generalize this definition one dimension higher, then it becomes difficult because we don't know what are the right coherences that we need to ask in one dimension higher. And because of this, we are going to take inspiration from another definition of stack, so a characterization of the notion of stack that has been proposed by Ross Street. So we say that F is a stack if and only if for every object in the category and every covering sieve, the functor of precomposition with the covering sieve is an equivalence of categories. And the idea of this characterization is that this object that we have here on the left is equivalent to f of C by the Yoneda lemma, while this object on the right is the category of descent data. And so we are linking the category of the descent data to objects and morphisms in f of C. This is an equivalence of categories, so we know that is essentially surjective and fully faithful. And in particular, the essentially surjectiveness of this equivalence gives the fact that every descent datum is effective, while the fully faithfulness gives the condition that the stack is a sheaf on morphisms. And now we want to use this to generalize the notion of stack one dimension higher. But before we need to introduce all the data that we need. So we consider K a small 2 category with bi-isocomma objects. And I have to say that everything could be done for a bicategory instead. And the reason why I didn't do it for a bicategory is that you get even more complicated diagrams and you have more isomorphisms to take care of. But of course, every bicategory is equivalent to a 2 category. And so we are lucky in this sense. So given these 2 category, we say that a bisieve S over an object C is a fully faithful arrow from from R to Yoneda of C. And this definition is the definition given by Street. Here we notice that this arrow is not a natural transformation, but it's only pseudo-natural. And this means that our bisieve is closed under precomposition only up to isomorphism in this case. Moreover, here we are asking a fully faithful arrow, but we are not asking that this is injective on objects. And this is a bit bad because this is the condition that allows us to talk about sieves as collection of morphisms. So we want to work with this additional condition. And to do so, we notice that every bisieve is somehow equivalent to a bisieve that is also injective on objects. So for our purposes, we can always consider bisieves that are injective on objects. And we can use these bisieves to give a definition of bitopology on the two category K. Here I have to say that in the literature, sometimes when you have a two category and you want to put a Grothendieck topology on it, you just consider the Grothendieck topology on the underlying category of the two category. But this is not two-dimensional enough for our purposes, and so instead we use the definition given by Street for a bicategory. So a bitopology on K is an assignment for each object of the two category of a collection of bisieves that we call covering sieves in a way such that these three conditions are satisfied, and these are just the analog of the one-dimensional condition that we have seen before. So the first is saying that the maximal bisieve is a covering bisieve, while the second one is saying that covering bisieves are closed under bi-isocomma objects. And so instead of pullbacks, here we have an upgrade to bi-isocomma objects in dimension 2. And the third condition is just saying that being a covering bisieve can be checked locally. Okay, so what is a two-stack then? Given a trihomomorphism from K up to Bicat, and a trihomomorphism is just the natural notion of morphism between three categories, and this is functorial only up to adjoint equivalence. We say that this trihomomorphism is a two-stack if for every bisieve, the pseudofunctor given by precomposition of that bisieve is a bi-equivalence. And so this definition really generalizes Street's characterization of the notion of stack, and it looks quite nice, but the problem with this is that it is very implicit. So if we want to prove that something is a two-stack using this definition, this is going to be a nightmare. We really need some explicit conditions that we can check more easily. And as I was saying before, it would have been very difficult to give a definition with explicit conditions because we don't know what are the right coherences that we want to ask. But now that we have this definition produces the right coherence conditions. And this allows us to find the right explicit conditions that we want to ask for a two-stack. And so, again, the idea is that we want to use the Yoneda lemma to do this. And we are lucky because Bounet, in his PhD thesis, proved a tricategorical version of the Yoneda lemma. So it says that if we have a trihomomorphism for every C in the two category here, we have a bi-equivalence between f of C and these objects, which is given by the three transformations from Yoneda of C to F. And this biequivalence is also natural in C. So explicitly, given an object in f of C, X, this will correspond to a tree transformation from unit of C to F. And this tree transformation has as component D, something that sends a morphism F from E to D in F star of X. This is exactly what happens in dimension 1. Moreover, this biequivalence gives us a way to, given a morphism in f of C, to obtain a tree modification, and given a 2-cell in f of C, to obtain a perturbation. And so now we can give an equivalent definition for the notion of 2-stack that says that for every bi-sieve in the Grothendieck bitopology, the pseudofunctor obtained by composing the biequivalence given by the Yoneda lemma and the precomposition with X is a biequivalence. And so now the idea is that we will have our data here and we can relate them to objects, morphisms, and 2-cells in f of C to obtain explicit conditions. And in particular, being a biequivalence means that it is surjective on equivalence classes of objects, essentially surjective on morphisms, and fully faithful on 2-cells. And these are the 3 conditions that will give our explicit conditions that we want to obtain. So we'll see them separately. Let's start from the 2-cells. So the first thing that we're going to see is what it means that this biequivalence is full on 2-cells. And this will give us a condition of existence of gluings on 2-cells. So the data that we have here is a perturbation, and this perturbation gives us some 2-cells, alpha F, from F star of A to F star of B, where A and B are morphisms in F of C. And these 2-cells are compatible in the sense that alpha F, the descent along G of alpha F is alpha of F composed G tilde. And why I put this tilde, it's because we have seen that the bi-sieve is closed under precomposition only up to isomorphism. And so by F composed with G tilde, I mean the morphism which is isomorphic to F composed with G and is in the bi-sieve. And so this compatibility condition is saying that essentially G star alpha F and alpha F composed with G tilde are the same. So here we have an equality, and these 2-cells that we have are just given by the fact that F is a trihomomorphism. And then if we have this data, we can find a 2-cell alpha from A to B in F of C, such that F star of alpha is alpha F for every F. And so here we're saying that the matching families for 2-cells have at least an amalgamation. So this is alpha of the condition that we need to ask if we want to say that this 2-stack F is a sheaf on 2-cells. And the faithfulness will give the other half of the condition. So if we have 2-cells alpha and beta that agree locally, then they are the same 2-cell. And so the fully faithfulness on 2-cells gives us the fact that the 2-stack is a sheaf on 2-cells, which is something that we want. Okay, we expected this. But what happens on morphisms? So on morphisms, we have an essential surjectivity, and this gives us the condition that every descent datum on morphism is effective. And this is, again, something that we we could expect to find. So what is a descent datum on morphisms? For every morphism in the sieve, we get a morphism WF from f star x to f star y. So instead of having objects as assignments, this time we have morphisms. And instead of having a compatibility condition given by isomorphisms, we have a compatibility condition given by invertible two cells. In particular, if we consider a chain of morphisms like this, where F is in the sieve, there is an invertible two cell like this one that relates the descent along G of the morphism associated to F with the morphism associated to F composed with G tilde. And these equivalences that we have here as vertical morphisms are just given by the fact that F is a trihomomorphism. But now we not only have morphisms in the sieve, because we also have two cells in this two-dimensional version. And so for every two cell, we will have an assignment of an invertible two cell between the morphisms associated to the domain and the codomain. Not really, but kind of this condition. And these two cells needs to satisfy some compatibility conditions. And all these conditions are given by the fact that we are considering a tree modification. So these are given by the axioms of a tree modification. And now we also need to have a cocycle condition on morphisms. And this cocycle condition is precisely given by the fact that the structure cells of the tree transformation are pseudofunctorial. And this cocycle condition, I'm not showing you the explicit condition, but it relates these two cells that are the same objects that we found in dimension 1. So this is about the descent along G, this is about the descent along H, and this is about the descent along the composite of G and H. Moreover, the same pseudofunctoriality of the structure cells gives us a condition that involves the descent along the identity, which we didn't have in dimension 1. So it's a new condition. And now we can say what it means for this descent datum on morphisms to be effective. And this means that we can find a morphism W, so our global datum is now a morphism instead of an object. And for every morphism in the sieve, an invertible two cell between the descent along F of the global morphism W and W of F. And this choice of two cells is compatible. And we have that given a morphism G, we have this natural condition, which is the analog of the condition that we had for objects in dimension 1. It relates the same data, and this two cell epsilon is a canonical two cell given by the fact that F is a trihomomorphism. So again, we have the same condition, and we notice that here our conditions are equalities. And now we want to see what happens for objects. And for objects, we have a surjectivity up to equivalence classes. And this gives a condition that I have called every weak descent datum is weakly effective. So to see what a weak descent datum is, we need to consider a tree transformation. And this gives us, for every morphism in the sieve, an object WF. And for every pair of composable morphisms, this time we have an equivalence between the descent along G of W of F and W of F composed with G tilde. So in this sense, I say that this descent datum is weak, because instead of an isomorphism here, we only get an equivalence. And moreover, again, we need an assignment for two cells, because we have two-dimensional sieves. And so for every two cell, we get a morphism, and this assignment is pseudofunctorial. And now we want to find the weak cocycle condition, and this weak cocycle condition is given by the pseudofunctoriality of the structure two cells of the tree transformation that we are considering. And I call it weak because here we have an invertible two cells, so this diagram is not commutative anymore, but is essentially the same diagram. So it relates the descent along G, the descent along H, and the descent along the composite. But here we have two different vertical morphisms here. This is due to the fact that F is a trihomomorphism, and so it's similar to the one that we had in dimension 1, while this is a new thing, because this is related to the fact that the bi-sieve is closed under precomposition only up to isomorphism, and moreover, this uses the assignment of the descent datum on two cells. So it's a new thing. Moreover, the same pseudofunctoriality gives also a condition that involves the descent along the identity and some additional coherence conditions. And so, considering the surjectivity on equivalence classes of objects, we get what it means to be weakly effective. So this means that there exists an object, W, in f of C, and for every morphism in the sieve, this time an equivalence between WF and F star of W, such that given morphisms F, given a morphism G, we can find an invertible two cell like this. And so again, this is the condition which looks similar to the cocycle condition. The only difference is that here we have an equality instead of an isomorphism. And moreover, we need to ask some additional coherence conditions that are again given by the coherence axioms of a tree transformation. And so we have found all the explicit conditions that we can ask to have a two-stack. And these are much easier to check in practice than the implicit definition. And I want to conclude the talk by saying why I care about this notion of two-stack and why I introduced it. And this has to deal with quotient pre-two stacks. So I had this object that I call quotient pre-two stack. It is a trihomomorphism, in particular a tree pseudofunctor, which is a bit stricter than a generic tree homomorphism. It doesn't really matter how this is defined. Essentially, it sends every object in a category of principal G2 bundle, two bundles. The important thing is that this object generalizes quotient stacks. It's the natural generalization of quotient stacks one dimension higher. And so I wanted a definition of two-stack that is suitable for this three-dimensional object. And I think the definition I'm proposing is the right one. But the proof that quotient pre-two stacks are two stacks is still work in progress. It's almost finished, but not yet. And so I hope to prove that this is a two-stack according to my definition. And this is everything I wanted to say. So thank you very much for your attention.
Thank you, Elena. Let's thank our speaker. And are there any questions? Yeah, go ahead, Ettore.
Yeah, I have a question. Very, very interesting. Thank you. So I'm curious about your motivation of a quotient two stack, and also in relation to the bi topology that you are considering, because I have. I mean, there is a very well-defined notion of two stack when you are in the presence of just a Grothendieck topology, and not not something so general as you define. So I'm curious about what kind of examples you are considering, where you are considering quotient two stacks or two stacks in for a bi topology. So what is an example of a concrete situation that does require the generalization that you are considering?
Okay, so basically I had this object, the quotient pre-two stack, and I wanted a notion that really captures the gluing conditions that are satisfied by these objects, that are stronger than the conditions that we obtain if we only consider a topology on the underlying category. And also everything I'm doing is bicategorical in nature. So if I have a bicategory, I really want to consider a two-dimensional Grothendieck topology. So I don't have other examples yet. I only have this quotient two stacks for now. I hope to find other examples. But thank you for the question.
Okay, thank you.
Go ahead, Doretta.
Very nice talk, Elena. Thank you. I enjoyed what you were doing. I have a bit more of a speculative question, but I'm just wondering whether you might have thought about it. So when I think about stacks and I think about quotient stacks, I think often in terms of geometric stacks that are represented by groupoids. So then it's also clear what you want to take as what is the quotient aspect of this. I'm wondering, do you have something similar in mind for your higher version? Do you have something of a generalization of groupoid that's going to fit an idea of geometric, maybe just in thoughts, not entirely worked out yet, of course?
Yeah, this is a very good question. I don't have this notion of groupoid yet, but is something that I'd like to explore because I think there is, and I think it's very interesting. So this is future work.
Thank you.
Go ahead, Simon.
Hi, yes, very nice talk. So when I think what you're talking about is very closely connected to the descent condition. Like stacks are basically objects that satisfy some kind of descent condition. But when I look at functor from a bicategory or two category to cat or bicat, I can ask for a descent condition or I can ask for a lax descent condition. Do you know if there is a way to recover some kind of lax descent from what you're doing, or if that needs to be generalized further?
Okay, I must say I'm not an expert in descent theory. I know that there are links between this and descent theory, and I know that two-dimensional descent theory is not studied so much yet. So I think there are lax versions of descent conditions, but I haven't worked about this yet.
Oh, okay. Thanks.